All right, so the first one is satisfied. The last one, the second one is the one that we're going to take a look at probably next Wednesday, the day before the finals. The alternate timelines is the one that we're interested in. Is there any evidence for such a thing?
Experimental physicist Andrew Cleland may have become the first man to catch a glimpse of a parallel universe. Inside this small square of silicon, Andrew has etched a barely visible metal panel. It's made up of over 1 trillion atoms. In the quantum world, it's Godzilla. And he's trying to show that something this large still obeys the rules of quantum mechanics.
We're very familiar with the fact that quantum mechanics applies to small things like electrons or atoms, but the idea that it should also apply to large things, things that we deal with in our everyday life, is much harder to accept.
But proving that his panel can behave quantum mechanically means making sure nothing measures it. It needs to be in complete isolation and very cold.
So this instrument is a dilution refrigerator, and if you have $500,000 lying around, you too could own one in your own home. The instrument has a series of temperature stages that go from 1 Kelvin to 0.6 Kelvin to 0.1 Kelvin, all the way to 20 millikelvin, or in other words, about minus 459 degrees Fahrenheit. This is where we operate these quantum experiments.
Inside the dilution refrigerator, Andrew directs a single quantum of energy at the paddle. It should have a 50-50 chance of either receiving the energy or missing it. Instead, to his amazement, the paddle both receives the energy and misses it at the same time, and begins to oscillate between these two realities.
The paddle can be both in a state where it has no energy and where it has one of these units of energy in it. And in that state, actually, when it's in both at the same time, you actually do get a vibration at 6 billion times a second.
Andrew's groundbreaking experiment proves that the strange laws of quantum mechanics govern everything in our universe, from tiny particles.
The paddle can be both in a state where or in other words, about minus 459 degrees Fahrenheit. This is where we operate these quantum experiments.
Inside
minus 459 degrees Fahrenheit. Kelvin, all the way to 20 millikelvin, or in other words, about minus 459 degrees Fahrenheit. This is where we operate these quantum experiments.
Inside the dilution refrigerator, Andrew directs a single quantum of energy at the paddle. It should have a 50-50 chance of either receiving the energy or missing it. Instead, to his amazement, the paddle both receives the energy and misses it at the same time.
All right, guys, I got news for you. Time travel is impossible. I would have said no, impossible. I wasn't even interested in teaching this course in its original form because I thought this was complete nonsense until I saw this. All right, past, the future, the present, all existing at the same time. Yeah, I got it. I don't care. Space-time flat curve, being able to take shortcuts. As far as I was concerned, that was science fiction, so I didn't care about that either. Only way you can do time travel is if there are parallel universes. The act of time travel needs to create its own parallel universe. This course was originally intended as an investigation. The end result was supposed to be that the time travel is impossible. That's it. That's what I was going for. Until I saw this evidence, the experiment. These guys are working on quantum computers, and they're running these experiments near absolute zero. That's negative 450 Fahrenheit. And this experiment absolutely blew my mind.
And
what you guys are looking at, this paddle receiving energy and not receiving energy at the same time, is exactly identical to tossing a coin. What are the chances that it's going to be heads? 50%. What are the chances that it's going to be tails? Still 50%. Until when? Until you look at it, guys. Until you look at it. Tossing a coin is going to have two possible outcomes. There's a 50% chance that it's going to be heads. There's going to be a 50% chance that it's going to be tails until you look at it. Upon looking at it, those possibilities will collapse into one of the realities. Either it's going to be 100% heads or 100% tails. Evidently, if you repeat the same experiment near absolute zero, which is negative 450 degree Fahrenheit, here's what happens. You toss the coin and look at it. What do you see? You see both outcomes at the same time. You will see heads and tails at the same time. That's what it means. You will see both universes at the same time. Which means that if you were to roll a die and you have 6 possible outcomes, 1, 2, 3, 4, 5, and 6, what do you see? All 6 possible outcomes. You will see all 6 outcomes at the same time. And this weirdness happens only near absolute zero. And that's what they discovered. And that's the sort of evidence that I was looking for. So near absolute zero, you see all these weird parallel universes, evidently. If there are 2 outcomes, if there are 2 possible outcomes, you will see both of them. This experiment that you just watched is Andrew Cleland. Currently, he's over at the University of Chicago. He's working locally. He moved up, evidently. He was somewhere else. The University of Chicago is one of the best places where you can work. That was... He's not the original guy who did the experiments. He's actually repeating this guy's experiment.
This is a representation of your brain, and your brain can be broken into two parts. There's the left half, which is the logical side, and then the right half, which is the intuitive. And so if we had a scale to measure the aptitude of each hemisphere, then we can plot our brain. And for example, this would be somebody who's completely logical. This would be someone who's entirely intuitive. So where would you put your brain on this scale? Some of us may have opted for one of these extremes, but I think for most people in the audience, your brain is something like this, with a high aptitude in both hemispheres at the same time. I mean, it's not like they're mutually exclusive or anything. You can be logical and intuitive. And so I consider myself one of these people, along with most of the other experimental quantum physicists. We need a good deal of logic to string together these complex ideas, but at the same time, we need a good deal of intuition to actually make the experiments work. How do we develop this intuition? Well, we like to play with stuff, so we go out and play with it, and then we see how it acts, and then we develop our intuition from there. And really you do the same thing. So some intuition that you may have developed over the years is that one thing is only in one place at a time. I mean, it even sounds weird to think about one thing being in two different places at the same time, but you weren't born with this notion, you developed it. And I remember watching a kid playing on a car stop. He was just a toddler and he wasn't very good at it, and he kept falling over. But I bet playing with this car stop taught him a really valuable lesson, and that's that large things don't let you get right past them, and that they stay in one place. And so this is a great conceptual model to have of the world, unless you're a particle physicist. It'd be a terrible model for a particle physicist because, well, they don't play with car stops. They play with these little weird particles. And when they play with their particles, they find they do all sorts of really weird things, like they can fly right through walls, or they can be in two different places at the same time. And so they wrote down all these observations, and they called it the theory of quantum mechanics. And so that's where physics was at a few years ago. You needed quantum mechanics to describe little tiny particles, but you didn't need it to describe the large everyday objects around us. This didn't really sit well with my intuition, and maybe it's just because I don't play with particles very often. Well, I mean, I play with them sometimes, but not very often. And I've never seen them. I mean, nobody's ever seen a particle. But it didn't sit well with my logical side either, because if everything is made up of little particles, and all the little particles follow quantum mechanics, then shouldn't everything just follow quantum mechanics? Yeah, I don't see any reason why it shouldn't. And so I'd feel a lot better about the whole thing if we could somehow show that an everyday object also follows quantum mechanics. So a few years ago, I set off to do just that. So I made one. This is the first object that you can see that has been in a mechanical quantum superposition. So what we're looking at here is a tiny computer chip, and you can sort of see this green dot right in the middle, and that's this piece of metal I'm going to be talking about in a minute. This is a photograph of the object, and here I'm going to zoom in a little bit. We're looking right there in the center, and then here's a really big close-up of the little piece of metal. So what we're looking at is a little chunk of metal, and it's shaped like a diving board and sticking out over a ledge. And so I made this thing in nearly the same way as you make a computer chip. I went into a clean room with a fresh silicon wafer, and then I just cranked away at all the big machines for about 100 hours. For the last step, I had to build my own machine to make this swimming pool-shaped hole underneath the device. This device has the ability to be in a quantum superposition, but it needs a little help to do it. Here, let me give you an analogy. You know how comfortable it is to be in a crowded elevator? I mean, when I'm in an elevator all alone, I like do all sorts of weird things, but then other people get on board, and I stop doing those things because I don't want to bother them or frankly scare them. So quantum mechanics says that inanimate objects feel the same way. The fellow passengers for inanimate objects are not just people, but it's also the light shining on it, and the wind blowing past it, and the heat of the room. And so we knew if we wanted to see this piece of metal behave quantum mechanically, we're going to have to kick out all the other passengers. And so that's what we did. We turned off the lights, and then we put it in vacuum and sucked out all the air, and then we cooled it down to just a fraction of a degree above absolute zero. Now, all alone in the elevator, the little chunk of metal was free to act however it wanted. And so we measured its motion. We found it was moving in really weird ways. Instead of just sitting perfectly still, it was vibrating. And the way it was vibrating was breathing, something like this, like expanding and contracting bellows. And by giving it a gentle nudge, we were able to make it both vibrate and not vibrate at the same time, something that's only allowed with quantum mechanics. So what I'm telling you here is something truly fantastic. I mean, what does it mean for one thing to be both vibrating and not vibrating at the same time? So let's think about the atoms. So in one case, all the trillions of atoms that make up that chunk of metal are just sitting still. Now at the same time, those same atoms are moving up and down. Now it's only at precise times when they align. The rest of the time, they're delocalized. So that means that every atom is in two different places at the same time, which in turn means the entire chunk of metal is in two different places. I think this is really cool. I mean, really. It was worth locking myself in a clean room to do this for all those years. Because check this out. The difference in scale between a single atom and that chunk of metal is about the same as the difference between that chunk of metal and you. So if a single atom can be in two different places at the same time, that chunk of metal can be in two different places, then why not you? I mean, this is just my logical side talking. So imagine if you were in multiple places at the same time. What would that be like? How would your consciousness handle your body being delocalized in space? There's one more part to the story. So when we warmed it up and we turned on the lights and looked inside the box, we saw that the piece of metal was still there in one piece. And so, I had to develop this new intuition that it seems like all the objects in the elevator are really just quantum objects, just crammed into a tiny space. You hear a lot of talk about how quantum mechanics says that everything is all interconnected. Well, that's not quite right. It's more than that. It's deeper. It's that those connections, your connections to all the things around you, literally define who you are. And that's the profound weirdness of quantum mechanics. Thank you.
All right, so there's supporting evidence for the alternate timelines. Andrew Cleveland's vibrating and non-vibrating paddle near absolute zero. So this happens near absolute zero. So why does the temperature matter? All right, so let's go in that direction just briefly. Let's discuss temperature. All right, so this is known as thermodynamics, which means that it's the study of heat and its relationship to the mechanical energy of the molecules, guys. So we're dealing with molecules and their mechanical energy. So what's mechanical energy again? It's the combination of kinetic and potential energies of the molecules. So what is heat and how it is related to the mechanical energy of the molecules. So that's what we're going to be focusing on.
For example, people tell you to put flowers in the refrigerator. Well, the extreme cold of liquid air really isn't very good for flowers. Let me show you. Interestingly enough, it doesn't change the way the flowers look very much. When I pull them out, they look pretty much the same, but it has made them just a little bit brittle.
So why did the flowers become brittle? What's the first thing that comes into your minds?
Frozen.
It's frozen, right? What got frozen? Water inside flowers, right? All right, so everything is made up of cells. Cells are about 70% water. So what happens to the water? It freezes. All right, that's the first thing that comes to your minds. Now, is this the right way of looking at it? We'll just find out. All right, Jen, give yourself for that one. Let's talk about temperature first. So what's temperature? Temperature is a measure of how hot or cold something is, right? So how do you know how hot or cold something is? You can measure it. How do you measure it?
No
Is it
one
thermometer?
needs to suffer with the flu. Doctors can now write prescriptions for a medicine that can actually shorten the duration of the flu. With first symptoms.
So we use a thermometer, but speaking of thermometers, there are 3 kinds of scales that we have to play with. All right, one in the United States that we use, obviously the Fahrenheit scale. Outside of the United States, Celsius scale is being used. In sciences, we use Kelvin scale. So we got 3 different scales. And what are the differences? All right, thermodynamics has got 4 laws, and there's a reason why we have to measure temperatures. All right, there are 4 different laws. And the first one is known as the zeroth law of thermodynamics. All right, don't copy this down as this, because this is meant for nerds, meaning that this is for engineering and physics students. I'm gonna just make it a little bit more simple. The reason why you measure temperature is because if there's no temperature difference, there's no heat flow. And if there's temperature difference, there's gonna be heat flow. Does that make sense? Right, so if there's no temperature difference, no heat flow. If there's temperature, then if there's no temperature difference, there's no heat flow. If there's temperature difference, then the heat is gonna flow from hot to cold. So what's heat? Heat is obviously a form of energy that's gonna flow from hot to cold. That's what it means. All right, so you guys will get to take notes over here. So what's thermodynamics? Thermodynamics is a study of heat and its relationship to the mechanical energy of the molecules. What's temperature? Temperature is how hot or cold something is. It's a measure of how hot or cold something is. So it's a measurement. So we got 3 temperature scales. You got Fahrenheit, you got Celsius, as well as you got Kelvin. So which one is being used in the United States? We got the Fahrenheit. Outside of the United States, we got Celsius. In sciences, we use Kelvin. All right, so what is the zeroth law of thermodynamics? The zeroth law simply says if there's no temperature difference, there's no heat flow. All right, so that's what it means. If there's no temperature difference, there's no heat flow. If there's temperature difference, the heat is gonna flow from hot to cold, so that becomes the second law. Okay, I don't see the second law here, but just make a note of it.
Could you repeat that again?
All right, so if there's no temperature difference, there's no heat flow. If there's temperature difference, the heat is gonna flow from hot to cold. All right, so that's known as the second law. So question number 18, we're skipping around. So what's heat? Heat is energy that flows from hot to cold. Just heat is energy that flows from hot to cold. So what causes heat? The temperature difference does. That's it. So what is heat? Heat is a form of energy that's gonna flow from hot to cold. So what causes heat? A temperature difference does. All right, so it's gonna flow from hot to cold. So according to the zeroth law, if there's no temperature difference, there's no heat or heat flow. That's what it means. So question number 8, what purpose does the measure temperature serve in thermodynamics? Well, you measure the temperature, check to see if there's any temperature difference, right? If there's temperature difference, there's gonna be a heat flow from hot to cold. This thing is very commonsensical. And if there is no temperature difference, there's no heat flow. So there would be no heat flow. All right, so if I'm drinking my coffee, if it's colder than, if it's hotter, shit. All right, if it's hotter than the room, what happens? It's gonna cool down, which means that the heat is gonna flow from coffee to the room until there's no temperature difference, which means that until the coffee is at the room temperature. So until there's equilibrium in temperature. So temperature difference means heat flow, no temperature difference, no heat flow. And that's as far as it goes. All right, so based on what we just discussed, pick out the best answer and justify it. Hey, Isabella, do you see the high-pitched sound still?
Yeah, I can still hear it.
Okay, so
Yeah.
is it coming from the computer or is it coming from the background?
I think it's coming from the background.
All right, so that's the water boiling. Okay, cool. it's not the connection. All right, give yourself 2 points for that one. All right, so in order to understand the concept of temperature, it's necessary to understand what? Okay, we've been talking about zeroth law, right? And we're also talking about the second law. If there's temperature difference, heat is going to flow from hot to cold, so that's the second law. If there's no temperature difference, there's no heat flow. And obviously, thermodynamics in general is related to heat and its relationship to the mechanical energy of the molecule, right? So it's got to be all of them. It's got to be the zeroth law, the first law, the second law. So D is the best answer. So test bank likes A, reality D is the best answer. All right. All right, take a short little break, and then we'll take it from here. All right, I'll see you guys in 10 minutes. All right, let's move forward. All right, so we're studying thermodynamics. So that's the study of heat and its relationship to the mechanical energy of the molecule. So we're dealing with molecules and mechanical energy, meaning their kinetic energies as well as their potential energies. So how does heat actually affect the kinetic as well as the potential energies of these molecules? All right, so what's heat? Heat is a form of energy that flows from hot to cold. So according to zeroth law of thermodynamics, if there's no temperature difference, there's no heat flow. And if there's temperature difference, heat is going to flow from hot to cold. That becomes the second law. Speaking of measuring temperature, so temperature is how hot. It's a measure of how hot or cold something is. There are 3 temperature scales. We got the Fahrenheit scale that we use in the United States. Outside of the United States, it's the Celsius. In sciences, we use Kelvin. All right, so the question is the difference between the Fahrenheit and the Celsius scale. Our Celsius scale is the one which is being used outside of the United States. In the United States, we use the Fahrenheit scale. And both scales are set up based upon the freezing point of water. On the Celsius scale, it's going to be 0. Fahrenheit scale is going to be 32. And then the boiling point of water, the Celsius scale is going to be 100 degrees, and Fahrenheit scale is going to be 212. All right, Fahrenheit scale versus the Celsius scale, they're more or less the same, except the Celsius scale is divided into 100 little pieces, and the Fahrenheit scale is calibrated into 180 small pieces. So as usual, in terms of the scales, what people use outside of the United States is a lot more logical than what people use in the United States. And so when it comes to Celsius scale, it's a much more logical scale than the Fahrenheit scale. So, but the measurements are done the same way. Kelvin scale is a different matter. All right, Kelvin scale is the one that we use in the United States, not in the United States, in sciences. And how does that work? All right, so speaking of the Kelvin scale, it's going to be related to the following. Kinetic energy, the energy of motion. We discussed that before. All right, skip 10, move on to 11. Your tire pressure, where does it come from? You get the tire pressure from the air inside, right? So if the tire pressure is not high enough, if the tire is going flat, what do? You put air into the tire. So what causes the tire pressure? The air molecules do. All right, more air molecules you put into it, the larger the tire pressure is going to be. So the next question, what happens to the tire pressure when the tires are heated? When you heat up the tires, what happens to the tire pressure? It goes up. So the next question is, why does the tire pressure go up? Well, you're not putting in more molecules in, and somehow magically the tire pressure is going up. And immediately you can put 2 and 2 together. The tire pressure is going up because of the simple reason that the molecules are moving faster. That's it. So what happens to the molecules when they're heated? They simply move faster, which means that they're kinetic energies will go up, which means that the pressure that they exert on the boundary of the tire is going to go up. So which means that the tire pressure within is going to go up. All right, so there's a simple logic to what goes up. So you increase the temperature. All right, so you increase the temperature. When you increase the temperature, the molecules will move faster. So that's their speed. Because they're moving faster, their kinetic energies will be larger. And because their kinetic energies are larger, the pressure, the tire pressure is going to go up. All right, so we got this weird relationship. All right, temperature goes up, the molecules are moving faster, larger kinetic energy, higher pressure. All right, once again, increase the temperature, molecules move faster, higher kinetic energy, larger pressure. Reduce the temperature, molecules are not moving as fast, lower kinetic energy, lower pressure. All right, immediately we make that connection. All right, notice that by measuring temperature, you're in essence measuring the average kinetic energy of the molecules. So all of a sudden we got this weird expression about temperature. So the temperature is related to the average kinetic energy of the molecules. So temperature is a measure of the average kinetic energy of the molecules. What that means is if the molecules are moving faster, temperature is going to be higher. All right, so you will end up measuring higher temperature for that environment, and vice versa. All right, increase the temperature, also the molecules will be moving faster. All right, pick out the best answer. All right, guys, whenever you're ready, just jump in.
Is it D?
D.
Oh yeah, D is the best answer. Those of you guys who picked D, give yourselves 5 points. And the rest of you guys give yourselves 2 points if you pick D. All right, average kinetic energy of the gas molecules, right? So the temperature is the measure of the average kinetic energy of the gas molecules. Mm-hmm. All right, now we have a better understanding of the frozen flowers.
There's one more thing I'd like to try at this temperature, and that's a football. You know, people do play football games in these incredibly cold climates, like Green Bay, Wisconsin, where the temperature can be 40 degrees below zero. And I often worry about that. And I don't worry so much about the football players. After all, they get paid plenty for doing that. And I don't worry about the fans, because anybody who would go to a game on a day like that deserves exactly what he gets. And I don't even worry about the sportscasters, because they're probably inside of a warm broadcast booth behind a plate of glass where they're perfectly safe. What I really worry about is the football itself. Because it does seem to me that being that cold can have an absolutely shattering impact on a football.
All right, notice that the football does not have any water in it, right? It doesn't have a cellular structure, so no water was frozen in it. So how did the football become so brittle, so fragile? What happened to the molecules inside when he reduced the temperature to temperatures near absolute zero?
The particles slowed down.
Particles slowed down, the connections became much more rigid, right? Give yourself 5 points for that one. Absolutely. And that's exactly what happened to the rose petals as well. It wasn't necessarily the water froze, which it did, but also every other molecule slowed down. So the connection became a lot more rigid. So that's what happens. The temperature measures the average kinetic energy of the molecules. So the molecules end up slowing down quite a bit. So Kelvin scale, Kelvin is this guy, he's the Lord Kelvin. His name is William Thomas. He's the one who came up with the Kelvin scale. The lowest temperature on the Kelvin scale is known as absolute zero. Absolute zero is the 0 Kelvin. All right, so what happens at 0 Kelvin? All right, let's just move forward. Is this. We'll take a look at it shortly. 0 Kelvin is the lowest temperature on the Kelvin scale. All right. Speaking of the Kelvin scale, interior of the hottest star, 10 to the 9. If you have 10 to the $9 in your bank, how much money would that be? Once, going twice. How much money would that be, guys, if you have 10 to the $9 in your bank? Is it about 10 bucks? 10 to the $9, how much money would that be? All right, I think we have problems here. 10 to the 9 is $1 billion. That's like $1 billion in your bank account. All right, so interior of the hottest star, stars in this case, it's 1 billion Kelvin, just think of it. Center of the sun, this is 15 million Kelvin. And the hottest temperature attained in a laboratory is 60 million Kelvin. All right, notice the center of the sun is 15 million. Hottest temperature that we were able to attain in a laboratory is 60 million. Center of the H-bomb explosion, this is 100 million. Notice that the temperatures that we're able to generate using modern physics, quantum theory, is almost 7 times hotter than the center of the sun. All right, this is the power of science, guys. This is the power of science. This is the power of quantum theory that we're discussing, which comes in 2 flavors. Obviously, you got the Copenhagen interpretation and the Minow's interpretation. Either way, they work. But I want you to focus on the lowest temperature attained in a laboratory. It's not 0. It's not absolute 0. It's very close to it, but it's not absolute 0. All right, so the question is, Why is it that it's not absolute zero? The answer to that question is because according to the third law of thermodynamics, absolute zero cannot be obtained. You can come very close to absolute zero, but you can never reach absolute zero. This is out of the question. Absolute zero can never be obtained. So what happens to pressure? Pressure is going to be zero at absolute zero. All right, so that's something that we need to focus on. Number one here, okay, let me take you through it once again. All right, reduce the temperature. Molecules are not moving as fast. Their kinetic energies are going to be small. The pressure goes down. That's what happens. So the lowest temperature that you can have is absolute zero. This is your Kelvin scale. So what happens? This is zero, no motion, no kinetic energy, no pressure. So the absolute zero cannot be reached. So the question is, why not? Why is it that we cannot reach absolute zero? Any ideas? All right. Question number 11. Where does the tire pressure come from? Tire pressure comes from air molecules, right? Larger the number of molecules that you have, more air you have, more the pressure is going to be. All right, it's common sense. So what happens to tire pressure when the tires are heated? Pressure is going to go up. Why does the tire pressure go up when the tires are heated? Because the molecules are moving faster. All right, so what's the relationship between the temperature and the average kinetic energy of the molecules? Higher the temperature is, faster the molecules are moving. Higher the kinetic energy is. In fact, the temperature is a measure of the average kinetic energy of the molecules. What's absolute zero? Absolute zero is zero Kelvin. What happens to pressure at absolute zero? No pressure, zero pressure. What happens to the average kinetic energy of the molecules at absolute zero? Zero average kinetic energy, which means that the molecules are not moving. According to the third law of thermodynamics, it is impossible to lower the temperature of any system to absolute zero. Why is this statement true? All right, why do you suppose that statement is true, guys? Why is it that we cannot reach absolute zero?
Because then eventually wouldn't exist. I'm not sure.
Okay, who said that?
Rachel.
Okay, Rachel, why did you say that? That's an interesting statement.
Well, if anything is alive, anything, it's gonna have motion. It's gonna have heat. It's gonna have something. So if it's absolutely zero, which is impossible, then it wouldn't even be able to exist.
Okay, Rachel, I'm going to give you just 5 points for that comment. It's an interesting comment. So what you're saying is the reality would not exist. That's what you're saying, right?
Yeah.
Are you saying that the atoms and molecules would become non-existent? Is that the direction you want to go?
I believe so.
All right, that's not a bad statement. All right, just you made it a little bit too philosophical. So I want to arrive at this conclusion from a little bit more obvious standpoint. Okay, so what's heat? Energy that flows from hot to cold, right? So what causes heat? The temperature difference does, right? Okay, guys, space is 4 Kelvin. Space is really cold. That's like 450 degrees Fahrenheit negative. That's what we're dealing with. 4 Kelvin. Absolute zero is lower than 4 Kelvin. So if there is temperature difference, what happens? There's always going to be heat flow, right? One region is at 0 Kelvin. The other region is not at 0 Kelvin. There's always going to be heat flow from higher temperature region towards the lower temperature region. And if there's temperature difference, there's going to be heat flow. That's what it means. And hence the reason why you can never reach absolute zero, because for you to be able to reach absolute zero, there has to be temperatures lower than absolute zero. All right, so that was the thinking behind the third law. The guy who came up with the third law, his name is Nernst, came up with it in 1920s. He's a chemist. And so if you're a chemist, you would not be taken seriously by physicists. So a bunch of physicists in 1990s decided to prove Nernst wrong. They decided that, hey, we got technology today. We can isolate and insulate a region of space to a degree that there's absolutely no heat flow in or out of that system, more like into that system. So they figured that they could reach absolute zero, and they tried. And here's what happened. All right, we'll get there in a minute. So let's just go over some of the questions. All right, pick out the best answer. Whatever you guys are ready. So what's the best answer?
Is it C?
All right, C is the best answer. Give yourself 5 points. Those of you guys who pick C, give yourself 2 points. All right. Let's get back to heat. Once again, what's heat? Heat is energy that flows from hot to cold, right? This is hot. This is not as hot. Obviously, your body's hotter than ice, so heat is going to flow from hot to cold. So it's a form of energy that flows from hot to cold. Also, you can generate heat.
Miss Martinez, is this your cake spinner with a block of wood you used to slow it down?
Yes, Miss Grimble. That is my cake spinner.
Thank you. Now, Professor Parsons, what would you get if you leaned this block of wood against this spinning disc, like this?
That would be splinters. Oh, no. Okay, now I'm kidding. You would get friction.
Could you be more specific?
No, I could not. No, I'm just kidding again. I'll be specific. You see, friction is a force that tries to stop motion, and friction always causes heat.
Can you show us?
Sure. Jury, rub your hands together like this. Getting warm, isn't it? Feel the heat? Well, that's friction. It's also the friction between the floor and our feet that lets us walk. Now, if the floor was very slippery, the friction would be less and it would be harder to walk. And look at this. 2-1 scramble.
Okay, now watch the thermometer.
Hey, the temperature's going up a little.
What a workout. Yes, that's right. The temperature went up from the friction of water rubbing against water. In fact, I can feel the heat in my shoulder from the friction from moving my arm like that. Ouch.
Michaela, would you please touch the plate and see if it's getting warm?
Sure. Oh, yeah, it's definitely getting warm.
So maybe it gets a little warm. It would never get hot enough to melt the cake or burn the bottom of it.
Mr. Savage, you couldn't be more wrong.
I could be more wrong.
Right. A lot of friction means a lot of heat.
Miss Martinez, how long did you leave the block of wood rubbing against the cake spinner?
All night, Miss Grimble?
All night.
Yeah, but still, to melt a cake like that, you need a lot of heat.
Mr. Savage, have you ever seen a meteor streak across the sky?
You mean a shooting star? Of course, I love those. I always make a wish when I see one.
What do you wish for?
I can't tell you.
Right. Anyway, my point is, a meteor leaves a huge trail of flames as it flies through the sky because friction with the air heats up the meteor and then melts it.
All right, so we end up getting heat from friction, right? So the mechanical energy gets converted into heat. So how does friction cause heat? All right, guys, study this. So how does friction cause heat? Through friction, what happens to the molecules? They start vibrating, right? All right, faster they vibrate, higher their kinetic energies are, higher the temperature is. The bigger the temperature difference is between the room and the surface. So when there's temperature difference, what happens? Heat flow from hot to cold. So through friction, surfaces will heat up because the molecules are moving faster. Faster moving molecules will generate higher temperatures. Higher the temperature difference is, or larger the amount of heat that's going to flow from hot to cold. That's it. All right, so let's get back to the story of physicists trying to reach absolute zero. According to the third law, the absolute zero can never be reached as long as there's a temperature difference. If there's temperature difference, the heat is going to flow from hot to cold. So you cannot prevent the heat from flowing from a higher temperature region towards a lower temperature region. Except the technology is so advanced today that we can insulate and isolate a region of space just so that there's absolutely no heat flow into that region. So a bunch of physicists decided to reach absolute zero, and they decided to go down below it. And here's what happened.
You are watching a Nova Video Podcast.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one or there and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I can imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.
To learn more about the Bose...
So here's what they discovered. They cooled this substance to near absolute zero.
Matter can exist in various states.
And then as they start to approach absolute zero, when they start to come closer and closer to it, what happened was the molecules end up dissolving into waves. So the question is, waves of what? As they dissolve into waves, they also noticed that if they could see molecules, they could see the same molecule at multiple locations. So the particles started to appear at multiple locations, as illustrated.
States. Atoms at high temperature always form gas.
So the molecules literally dissolved into waves. And the first thing that they noticed was they were able to see the same molecules at multiple locations. So the question is, waves of what? Why would you see the same molecules at multiple locations? What's going on? And that's the reason why. Special effects.
If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid.
Notice that eventually he starts to appear at multiple locations himself. So he's going to appear at every single location where he could, probabilistically. When they shined a light onto the substance, which is known as Bose-Einstein condensate, otherwise known as the state of matter near absolute zero, light literally slowed down to a bicycle speed, probably about 20 to 30 miles per hour. Why did the light slow down? All right, so these are the questions we will get to investigate. It just so happens that absolute zero cannot be reached according to the documentary because the last bit of energy is going to take forever to extract from the system. How do we come up with those kind of weird conclusions? Where do we get our facts from? How do we know that the same atom or molecule appears at multiple locations near absolute zero? Besides these particles making up reality, the atoms and the molecules, dissolving into waves. Question is, waves of what? All right, so those are the things we will get to investigate. Speaking of waves.